Hello. Just give me 1 second, all right? Okay, so I hope everyone's doing fine. So you have transformed from a butterfly to a whale. Is that kind of a metamorphosis? Fair enough. Okay, we're about to begin with the session today. Okay, so it means that you were born as a butterfly and then you undergone metamorphosis to be a whale. Okay, that's cool. I mean, that's a great leap from an insect to a mammal. That's a huge leap, that is. Hello, hello. So let's get started with the lesson today. Yes, I'm good, thank you. And I hope you're doing fine as well. So what we will be doing today is the constructing and proving. So there's not much I can tell you about constructing and proving. We are just going to look through these questions and see how we can handle these type of questions, all right? Constructing is and proving is also very, very popular in the JMO. And there's going to be one proving question or construction question almost every year. So again, if you are getting it done, if you are like finding everything in today's lesson easy, it means that, well, congratulations on getting at least another one Section B problem in JMOs. And you're, again, one step closer to your trophies. Right. So that being said, let's get started. So if you still remember this question from yesterday, which is from the 2022 paper, this is actually, I'm not sure. I don't think they have real trophies though. So this question is a construction question because I would need to find a way to put these numbers into the rows and columns, right? So you can say that it's kind of like a numerical construction, which is like using the property of the numbers to construct the shape. So usually for construction questions, there will be two types of construction questions. The first type is the more number theory type one. And then the second type is the geometric type, which means that we need to draw some assisting lines there, for example, to construct some shapes and figure it out. All right. So let's see what we have here. Basically, this is one of those number theory type construction problems. So it says that I want to choose a list of n different numbers from the first 20 positive integers such that none of them is having a difference by 5. Okay. So none of the two numbers that I'm choosing is having a difference of 5. What is the largest value of n for which this is possible? So you can see that this first part of it is the construction part. So in order to do that, what we can do is to take the first 20 numbers and then put them into groups that have a difference of 5 first. So for example, 1, 6, 11, 16, 2, 7, 12, 17, 3, 8, 13, 18, 4, 9, 14, 19, 5, 10, 15, 20. So you can see that we have 5 sets of them, which they have a difference of 2, right? Difference of 5. So at most, how many numbers can you choose from each list that doesn't have a difference of 5? Is that just 1? 2, right? For example, if I'm taking 1, I can also take 11 or 16. Yeah. If I'm taking 6, I can also take 16. If I'm taking 11, I can take 1. If I'm taking 16, I can take 6 or 1, right? So among these 20 numbers, it means that I can choose at most 2 numbers from each set of 4. And also, I don't need to worry that these numbers are going to have a difference of 5 with the other groups. Does it make sense? So that's going to be everything for the construction. Once you're done with this construction, you can see that, well, across different groups, you're not going to find a difference of 5, right? So you just need to choose the numbers in the same group and see how many numbers you can choose at most. So that is going to be 10 for the maximum of n, all right? So that's for the first section. And then for the second section, it's basically counting. So I'm not that good at counting, but we're going to try to do this together. So how many different lists are there with this many numbers? So in each group, I can take 3 different options, 1, 2, and 3, right? So it means that I have 3 different choices for each group. I think that's right. So for the 5 groups, the number should be 3 to the power of 5, which is going to be 243. I'm not sure if that's correct, but I guess it is. But an important thing about this question is how you can construct these groups. So the counting is the extra part. All right. So that's for the first one. And then for the second one, you can see that's another question from the 2022 paper. So actually, the 2022 paper has a lot of construction questions. How can we have 5 different choices? Did I miss anything there? 111, 116, 6, 16, 11, 1, which is 111, and then, yeah, that's it. That's it. 3 for each of them. What exactly does construction mean in terms of knot geometry? Good question. It means that you need to, it's a little bit abstract. You need to form a structure. You need to provide a set of structure for your question. That's what it means by construction. So it's like you're not just doing the calculation, you're building a framework for the question such that when you are analyzing it through your framework, you can reasonably explain your answer. Why did I write 2? 2 is the number of numbers that I can choose for maximum. So that's sub-question 1. 2 is for sub-question 1. And 3 is the number of choices for that 2 numbers. That's for sub-question 2. Okay. All right, so let's take a look at the next question, 2022 B4. So I realized that they really like to have these kinds of construction or proving questions in 2022. And if things goes well, it might as well just be a similar standard this year. Because I would say that this year's paper might be having the same sector as the last year's one. Because, well, judging on the JMC paper, I would say that this year's paper is kind of similar to last year's paper. Somehow. But we can't be sure. So that's just a guess. Of course, you should do last year's paper. No, that's not a guarantee. That's just a guess, as I said. Bad guess? Probably. But well, it doesn't really affect how you're planning for this, right? It's okay, you still got time. And then it says that Seth creates n standardized by folding up n identical copies of the net shown, which doesn't really matter because it's a standardized, right? Which means that all the opposite faces are going to be 7. So given or not given the net, it doesn't really matter. But yeah, that's what it is. And then he repeatedly puts one of them on top of the other until there are none left, such that there is a vertical tower. And the question says that the 4 totals of the 4 vertical walls are all odd. So what are the possible values for n? So first of all, you need to do a little bit of construction there. Because we know that every 2 opposite faces adds up to 7, right? And if you break 7 into 2 numbers, like the sum of 2 numbers, it has to be an odd number adding an even number. So it means that for each layer, there's going to be odd, even, odd, even, odd, even. In each layer, there will be 2 odd numbers and 2 even numbers. Does it make sense? So it means that for any single layer, it is impossible. Does it make sense? Because I want the 4 totals to be all odd, right? And if I have 2 layers, of course, it means that I can do even and odd on top, even with odd on top, odd with even on top, odd with even on top, right? So that works. But then, of course, we can't analyze it one by one, right? So what about 3, 4, 5, so on? What are we going to do? So if I have stack a third one on top of the first 2, it means that in each layer, there will be 3 possibilities, right? Odd, 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 4 actually. Odd, even, even, odd, odd, even, and even, even, even. Yeah? So if I'm looking at these 2 possibilities, they will both be even. If I'm looking at the first 2 possibilities, they can be odd. Right? So now we are just thinking about, can they all be odd? So what do you say? First of all, can I have all the 4 stacks as 3 odds? Of course not. And then it means that, well, if I have 3 stacks, the total number of odds I have is 6, right? So technically speaking, I can have a column of odd and then odd, odd, odd in the 3 other columns where I have even, 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 even. Yeah? So we just need to arrange the odds now. So it means that, for example, if I have odd, odd, let's say for the 4 layers, for the 3 layers, if I have odd, odd, even, even in the first layer, I can have odd, odd, even, even in the second layer, and then odd, odd, even, even in the third layer, right? Technically speaking, we can. But in reality, is that possible? Nope. Because the odd cannot be opposite to odd. Does that make sense? In other words, the 3 opposite faces pairing up is going to add up to 7, 7, and 7. So if I have 3 sevens, the total is 21, which cannot be divided by 2, right? If I need to have 2 numbers adding up to 21, it has to be 1 odd and 1 even. The same goes for 35. The same goes for 49, which means that whenever you have an odd number of dice stacked up, it's impossible. Whenever you have an even number of dice stacked up, it is possible. So the possible values of n is even number. Does it make sense? So that's the odd even analysis. Well, you don't have to go through all that basically, if you just do the odd even analysis. So I was just doing these to show you why it is not impossible. How would I approach this question? Very good. Very good. That's a very good question. Because first of all, we know that if I am given this question, n is not given, right? So I don't know how many dice are there. I see. First of all, I don't know how many dice are there, right? And I don't know why I should classify it into odd and even, which is the reason why, first of all, we would try. Because this is a construction question. So now listen to me, everyone. For construction questions, we need to think about how to build it up. So first of all, we need to observe what kind of patterns it have, right? For example, if I'm looking at one of them, of course, it doesn't work. If I'm looking at 2 of them, it's going to work. If I'm looking at 3 of them, it doesn't work. And if I'm looking at 4 of them, it would be stacking up 2 of the 2s, right? So I can just stack up 2 of the 2s. So it's going to work. So essentially, you can just move on like that. Not stacking up 2 of the 2s, but like manipulating the 2s. For example, even, odd, odd, even. Something like that. So in the end, what we can see is that I sort of found a pattern of what can work and what cannot, right? Because 1 and 3 are odd and it doesn't work. 2 and 4 are even and they work. The reason why even works is that if I am stacking odd, even, they will be adding even numbers to the odd numbers for 2 dice, right? And no matter how many even numbers I'm adding to the odd number, it's always an odd number. So once I've proved 2 is right, all the next ones are right. All the next even numbers are right. And now I just need to prove that odd number of dice won't work. And we need to come up with an idea of why. Now we know that the opposite faces of a dice adds up to 7. So 7 is odd adding even. That's what we know in the very beginning, right? Because they can be in any arrangements. So it means that it's not specifically about some numbers. It has to be about the properties of these numbers, which is one of them is odd, the other is even. And then if 7 has to be split into odd and even, and that's the reason why you can't get both odds on the opposite sides, why don't we just try to expand it to 3 layers? So 3 of the 7s is 21, which means that on 2 opposite stacks or the two opposite walls, they must add up to 21, right? Which again, one of them has to be odd, one of them has to be even. And if it is 5, that's just the same, because 7 multiplying an odd number is always an odd number. And whenever I have an odd number and I want to break it down into 2 numbers, it has to be 1 odd and 1 even. Yeah. So this is the number theory kind of construction problems. It needs you to have some knowledge in number theory first. So like some knowledge and understanding with number theory. That's very important. So basically you can say that, you can see in the previous question, the framework is to put numbers which are, like 5 away from each other into groups. In this one, we are putting all the scenarios n into 2 groups, odd or even, right? So this is what we call construction, which is like to build a framework for the questions that we are trying to solve, and then try to explain it under the framework that we are building, provide a generalization for everything that we are trying to explain. So of course, it won't be that easy. You can start with trial and error. Parity. Yes and no, because it's not always about parity. So the first step for construction questions should be observing it first. Like observe the question and see what might be the pivot of the question. So like, how would you possibly try to approach it? Like, what properties does it have? Okay, so this kind of questions is pretty vague, which is the reason why I don't have anything solid to teach you today. But I hope that I can just try to inspire you a little bit on how you might be able to think about these questions. Okay, so in today's lesson, I'm just pretending that I have never seen these questions before. And I'm just trying to solve it from the very beginning. And this one is another one from 2022 B5. So you can see that the 2022 paper does involve a lot of these questions. It says that Charlie chooses one cell from a blank n by n square grid. So again, n by n means that it can be 1, it can be 999, it can be any number. Whenever you see this, you know that you can't possibly analyze it one by one, right? Because you can't calculate to infinity, which means that you always need a generalization for it, which is like in terms of n. Just like when you are having an arithmetic progression, you can't write it forever. That's the reason why we need a general term. So for an n by n square grid, if you shade one cell and the resulting grid has no lines of symmetry, how is that going to work? So basically, again, as I said, we need to observe it. The best way to observe it is through trial and error. So let's see if I have a 1 by 1 grid, which is literally just one box. Of course, there's nothing I can do about it, right? If I shade it, if I unshade it, it's just one square. Of course, it would have a line of symmetry. So no help here. Not helping at all. If I have a 2 by 2 square, can I shade any box in this one? Is it possible that I can shade any box in this one, such that it has no lines of symmetry? No, it's still impossible. if I shade this one, then there can be a line of symmetry like that, right? If I shade this one, the same. So it's just rotating it. So for the four of them, I can't shade it because the diagonals are having the lines of symmetry there. We know that a square has 4 lines of symmetry, right? And I can't fill in any of these boxes. What about 3 by 3 one? Well, the lines of symmetry goes all the way there, which means any box I shade, there will be a line of symmetry. 4 by 4. So I need to keep observing until I find a pattern. For 4 by 4 ones, well, you can see that the horizontal and the vertical lines of symmetry are going through, like the gaps between the squares. So it seems more possible this time because the lines of symmetry are only going through these boxes, which means that I have 1, 2, 3, 4, 5, 6, 7, 8 boxes that I can fill in. But that's just the first one that we are seeing. So we need more evidence, which means I should keep looking for more possibilities. For example, 5 by 5. Now you can see that for a 5 by 5 one, the lines of symmetry are not going through the gaps this time, right? So it means that there will be fewer boxes that I can fill in than the 4 by 4 one. I can just fill this one, 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 this one. So, oh, not this one. It should be this one. Still 8. It's still 8. And what about the 6 by 6 one? If I have a 6 by 6 grid, so the lines are going to go through the gaps again. So you can see that there will be more options that I can take. I can take 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So 24 of them. Yeah. So you are starting to find a pattern there. Whenever the n is an even number, the horizontal and the vertical lines of symmetry are going to go through the gaps. Whenever n is an odd number, it's going to go through the center. Right? So now you can see clearly this can be split into 2 scenarios for n. When n is even, which are the boxes that we can't take? It's the boxes on the 2 diagonals, right? So when n is even, what's going to be the number of the boxes on the diagonals? 1, 2, 3, 4 for one of them. 1, 2, 3, 4 for the other one. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So it's going to be equal to 2n. Or like the boxes I can't take is 2n. And how many squares are there in total? N squared. So how many different cells can be shaded? N squared take away 2n, or n times n take away 2, when n is even. So we can test that hypothesis with our conclusion. For the first one, n squared is 16. 2n is 2 times 4, which is 8. 16 take away 8 is 8. So that fits. For 1 to 6, n squared is 36. 2n is 12. 36 take away 12 is 24. Exactly the number we have just found. So this works. But then that's only concluding the case when n is even. Now we still need to do the case when n is odd. So it should be 1n, 2n, 3n, 4n. But the middle one has been counted 4 times, which means 3 extra times, because all the 4 lines of symmetry are converging at the center or intersecting at the center, which means that I need to remove 3 times that it has been counted extra. So I can't shade 4n take away 3, which means the answer is n squared take away 4n take away 3, which is n squared take away 4n adding 3. If you want to factorize it, feel free to do that. That's just n take away 1, n take away 3. Well, you don't have to do that. So let's test if that's right. N squared is 25. 25 take away 4n, 20 is 5. 5 adding 3 is 8. So that fits. If you're still unsure, just try 7 by 7 and count the number, and you will still get it. So that's how we can find the answer to these kinds of questions. As I said, first step, observation. Second step, generalization. So if you're just observing, no matter how many times, like no matter how many grids you're drawing, you still can't find the answer. Because you need to classify the cases that we are looking at and put it into conclusion, which means generalizing it. Does it make sense? So, any questions? For example, in this question, we are just classifying it into 2 categories, 2 different categories, odd or even, and you'll be able to solve them. And the reason why we have discovered this generalization is because the even ones are going through the gaps, the odd ones are going through the center. So clearly there's a difference, right? And for some geometric constructions, well, again, there's not much I can teach you about, just an observation. You just need to do an observation and construction. But then this question is already giving you the hint, like find the size of the angle DRQ. So if you are to do the size of DRQ, of course, you want to find out which angle it is first, right? So DRQ, it's that angle. So after that, you just need to observe it. And if you can see that this is parallel, this is going to be the same as X, right? And also, the 2 rectangles are the same. Why do they have to be the same? Like, what happens if they're not the same? So usually these kinds of information are very important. It means that we are using the property of it being congruent. So what's going to be the same if they're congruent? Of course, for any rectangles, the angles are the same, right? So what else are the same? The lengths. So we are making use of that, discovering that AD has the same length as AP. and that's isosceles. So it means that the base angles are both 180, take away x divided by 2. So that's 90 degrees, take away x over 2, which means DRQ is 90 degrees, take away 90 degrees, take away x degrees over 2, which is x degrees over 2. All right. So for the geometric ones, I would say it's more flexible. But the same thing works. Just try to observe it first, and then try to draw the assisting lines, which is actually going to help you. For this question, it is, again, a construction question. So probably we can come back to this later, given the short notice. Like, we don't have much time. I am a little bit surprised that we have already spent 40 minutes on this. But then we can just try to, well, I would say this is also one of the proving questions. But then we can just try to look at the more proving questions, because like the previous one is a little bit about construction as well. So for proving questions, you need to provide mathematical reasoning for your answer. It means that you cannot just give your answer without explanation. So you need to support your answer. So for example, in this question, it says that I am going through the squares, visiting the black and the white squares. So I need to go alternatingly between the black and the white squares. Is it these 5? I don't know. It might be a typo. So it's asking you the smallest number of white squares that I have to visit. And then we need to prove that it is indeed the smallest. Which means actually these two sub-questions are just the same sub-question. So you need to find a reasoning for that. Okay. So now you can see that there are a total of 10 black squares. Right? So starting from one of the white squares, the maximum number of black squares I can reach is 4. Does it make sense? Yeah, we only need 4. So if you are moving on from one white square to another white square with a connection of a black square, you can extend 3 extra, let me use another color. You can go with 3 extra black squares. So technically speaking, like theoretically speaking, the maximum number of black squares you can reach in 3 white squares is 10. But then why does it not work in this case? So think about if it is in a row like that, right? You can already have 10 black squares with 3 white squares. Or if it is going like that, Yeah. So why does it not work in this case? Well, yes. The reason is because these corner ones are attached to 2 white squares only. And these 2 white squares can only reach out to 3 new black squares. So if you are imagining that you're starting from one of these white squares, then the initial value you have won't be 4, right? So it means that the initial value you have is going to be 3 if you want to cover these corner ones. And then 3 adding 3 adding 3 is less than 10, which means that you would need at least 4 of them. Does it make sense? So you're just going to start with one of these 4 white squares to begin with our analysis. So it means that, well, if I want to cover the corner black squares, I must be taking one of these white, right? And starting from one of these whites, the maximum number of extra black squares I can reach for the next white square is 3. So if I'm reaching 2 more full capacity white squares, I can only cover 9 black squares. Yes, I know, we have to start from black square. But then the thing is that I need the white squares to connect the black squares, yeah? And it is asking you what is the smallest number of white squares that you need. So it's not about how you move. It's not about how you move. So if you think about this question as if you are moving it, then you have fell into the trap. You have fallen into the trap. Don't ever start to think about how you can move. Think about how you can connect the blacks with the whites. That's what the question is actually asking you to do. Because you would need the white squares to connect the black squares that you need to visit, right? So for example, if you need to get to the corner black square, you need one of these 4 squares, which is marked with a star. Okay. And this is a similar question in 2021. This is pretty easy. It says the integers 1 to 4 are positioned in a 6 by 6 square grid, and they cannot be moved. Now I'm filling in all the other integers into the empty squares. Prove that no matter how this is done, the integer in some pair of the adjacent squares must differ by at least 16. So that's pretty easy. Pretty easy. We just need to analyze these 16 boxes. I need 16 different numbers for these 16 boxes, right? Which means within these 16 numbers, the minimum value of the greatest number is 20. Because I already have 1, 2, 3, 4. And if I need 16 more numbers, the minimum of the greatest is 20 from A to P. Why? Because I need 16 more numbers apart from 1, 2, 3, and 4. So for the largest one, you would have to count up to 20, even if you are trying to be taking it as small as possible. You need to think about why it is 16. We have 4 numbers given, and the difference is at least 16 for the adjacent squares. So how many numbers does the 4 numbers have as the adjacent numbers? 16. So after writing all the 16 of them, you can see that the smallest value of these 16 numbers, of the maximum of these 16 numbers, is 20. It can't get any smaller than that. Otherwise, you can't have 16 numbers. So if the minimum of the maximum value is 20, it means that the maximum, like the minimum difference between 20 and 1 or 2 or 3 or 4 is definitely 16, which is equal to 16 already. So that's the proof. Because I need 16 numbers to be put in the 16 boxes. And that's B6. You see? So if you ever see these kinds of questions, that's just 5 minutes for 10 points in the JMO. All right. Of course, you can also analyze the next layer, but then it's not necessary. It's not necessary. If it is at least 21, then probably it's not true. Yeah. So that's basically what we have for this question. And then there's also one more thing that I want to tell you. Yeah, dominoes. So basically, there's a type of questions in proving, which is like the mathematical induction, like the MI. Well, actually, the mathematical induction in depth is for the further maths in high school, but this is the baby type of mathematical induction that you can do. So what's the steps for mathematical induction? The first step is make sure first domino falls. Right? That's what we need to do when we're poking a domino. The first step is to make sure that the first domino is falling. The second step is to make sure every consecutive domino falls. Which means if the first one falls, the second one should fall. If the second one falls, the third one should fall. I need to make sure that every following domino is falling, right? What about building it? We're building it in this way. We're exactly building it up to this logic, right? We are building it such that we are making sure that every following domino needs to fall once the first one is falling. So, what can we conclude after that? It means that if the first one falls, all falls. That's the outcome for mathematical induction, which is I just need to find a starting case. And the second step is to make sure that every following case is reasonable after the starting case. So every of the cases follows. Once you satisfy these two conditions, you can say that if the first one stands, all of the other cases stand. That's the logic for the mathematical induction method. And we have seen these kinds of questions, including 2016 B6, but that's not the only time. So this is a very famous question again. I guess probably you have seen it before. For which values of the positive integer n is it possible to divide the first 3n positive integers into 3 groups, each of which has the same sum? So first of all, if n is 1, 3n is 3, right? So 1, 2, 3. Can I have 3 groups of the same sum? Of course not. Of course not. So if n is 2, 3n is 6. 1, 2, 3, 4, 5, 6. So we can group it first to last, second to second last, third to fourth. Right? And then when n is 3, 3n is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we can do 1, 5, 1, 5, 9. Is that 159? Two, 4, 2, 4, 8. So 159, 2, 4, 8. Oh, that doesn't look right. Let me think about it. 1, 5. 159, 2, 6, 7, 3, 4, 8. Yeah, that's one of them. All right. Or any other methods. When n is 4, 3n is 12. So 1, 2, 3, 4, 5, 6. Well, we already know how to group it into 3 groups. If I have 6 more numbers, 7 to 12. I can just group it like that, right? And then combining with 1 to 6, of course, I can have 3 groups. And then if n equals 5, I will have 6 more numbers on top of that. I can also group it into 3 groups, right? So every time it's going to be adding 6 numbers to the previous cases, depending on whether n is odd or n is even. When n is even, all of them works. When n is odd, all of them works. So everything works except one. All right. So that is the logic of mathematical induction. First of all, I need to make sure that the starting cases are working, which are n equals 2 and n equals 3. And then we just need to make sure that we are finding a construction such that all the later ones are also working. Right? So for every 6 extra numbers, I can group it as 1, 6, 2, 5, 3, 4, which will always be the same. Yeah. So that's it for this question. And well, we can try to go back to this one. If you're still interested, you can just finish this one before you go. So for this one is from 2002. And it's question B4. It says that we have 1, 2, 3, 4, 5, 6 placed at the nodes. And we want to show a way of doing it or prove that it is impossible, such that I am having each line being the sum of the 2 numbers at the ends of the edge different. So first of all, let's just think about what are the possibilities. 1 adding 2 is 3. That's the smallest. 5 adding 6 is 11. That is the largest. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9 lines, right? So 3 to 11, there are 9 numbers. So, well, theoretically speaking, that is possible to have all different sums. So let's give it a try. So we can say 1, 2, that's 3. So if I need a 4, that's going to be 1 adding 3 because I can't do 2 adding 2. 2 adding 3 is 5. So then I need a 6. Then it's going to be 4 there. 7. And I need an 8. So that's going to be 8, 9, 10, 11. That's done. Easy, isn't it? So just do a random guess and you're already done. Just fill it in order. What's so hard about it? Like, I'm pretty sure that you can all finish this first part, but then for the second part, it requires a little bit of construction. So what is the construction in the second part? Again, we have 9 lines, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. But this time it's in a different arrangement. So we want to see whether it's impossible to do so. First of all, I need to fill in 3, 4, 5, 6, 7, 8, 9, 10, 11, which means there are 1, 2, 3, 4, 5 odd numbers, right? Usually, if the first one is working, the second one would not be working. So actually, going into this question, you know it is impossible. Like, it's rarely going to be possible for 2 sections. Otherwise, it won't set the question like this. It's just going to ask you a way to fill it up. So if you go into that, you just need to think about how to make it impossible. So for the 3 numbers at the 3 corners of each equilateral triangle, it can be all odds, all evens, odd, odd, even, or even, even, odd, right? There are 4 possibilities. If the 3 corners are all odds, it means that the outcome is 3 even numbers. for the 3 lines. Does it make sense? If the 3 corners are all evens, the outcome must be 3 even numbers as well. If it is 2 odd and 1 even, it means that the outcome would be 2 odd and 1 even. If it is 2 even and 1 odd, the outcome would also be 2 odd and 1 even. So what does it mean? It means that the number of odd numbers I would have in these 3 triangles would be a multiple of 2. Three, 5, 7, 9, 11. That's 5 odd. Is that a multiple of 2? Apparently not. So it's impossible. All right, so that's everything. That's everything for today. But then the thing is, usually, if you have a question which is asking you to either show a way of doing this or prove that it's impossible, and it has got 2 sections, if the first one is impossible, the second one is usually possible. If the first one is possible, the second one is usually impossible, unless the question setter is deliberately setting a trap for you, which has got like a 10% chance. So you can decide on your own whether you're going to take that chance or not. Right? Okay, so that's everything for today. And I hope that's helping. Well, I've never seen that before. All right, thanks everyone. And that's the end of today. Thank you all for coming. I'll see you next time. All right. Good luck. Bye-bye. Thank you.